Believe it or not, I started struggling in saying meteorologists. So I have gone back and started re-recording. Sometimes your brain just freezes, right? So there are a series of articles nowadays talking about how AI models are, more accurate, less error, much faster compared to the dynamic weather forecast models. And there are, many people claiming this, including Google, and now ECMWF has gone into some AI forecasting. So I'm going to just take a few articles and summarize them very briefly, because this is a hot topic and it's an exciting topic, because if indeed AI can give us faster and more accurate forecasts, then burning all those energy cycles by increasing model resolutions can be very helpful to mix at least AI. AI is not really ready to replace the dynamic models, but it looks very promising. So even K-scale model or 1 kilometer scale global model will probably need AI to analyze the output, because it's basically a big data problem at that point in terms of just how much output it will generate just in a few hours, a few days, let alone few months and few years. So this says here, 10-day artificial intelligence forecasts can match official predictions in a fraction of the time, right? Artificial intelligence is set to revolutionize weather forecasts. Cheap and fast algorithms are matching and surpassing the world's top models. It's a very short article, but I'm going to make it even shorter because I'm going to read a couple of other papers as well. Meteorologists call it the quiet revolution, a gradual but steady improvement in weather forecasting. Today, the 6-day forecast is about as good as the 3-day forecast from 30 years ago. Lots of data simulation and so on. Rarely do severe storms or heat waves catch people unaware. This revolution has saved lives and money, but also comes with a cost. Billions of dollars worth of energy-hungry supercomputers that must run 24/7 just to produce a few forecasts a day. Artificial intelligence is now spurring another revolution within numerical weather prediction, as the field is known. NWP, in mere minutes on cheap desktop computers, trained AI systems can now make 10-day forecasts that are as good as the best traditional models, and in some cases even better. The world's top weather agency, the European Center for Medium Range Weather Forecasts, has embraced the technology. Last month it began to generate its own experimental AI forecasts. Algorithms could enable more frequent forecasts and free up computing resources for other thorny problems. It's very, very exciting to know we can generate global predictions that are skillful really cheaply, says Mario Molina, an AI-focused research meteorologist at the University of Maryland, where I used to be for a long time. Of course, Molina moved from NASA, I think. Some of the world's biggest tech giants jockeying to claim the most skillful model, including Google DeepMind, which I'll read in the next podcast. Google DeepMind, which describes its GraphCast model in Science this week, and Huawei, which published a similar model called Pangu Weather in Nature earlier this year. So you can see everybody is getting into it. Google also has a short-term AI weather model that makes rolling 24-hour predictions that are more accurate than nearly any weather agencies. Nvidia is doing this now even faster, because they are the king of GPUs, graphical processing units, which can accelerate computations incredibly over compared to the traditional chips. It's incredible progress on a task that was thought infeasible just a few years ago, says Aditya Grover, an AI researcher at the University of California, Los Angeles. From a technology standpoint, we have all the ingredients in place. Jump ahead. The new AI models skip the expense of solving equations in favor of deep learning. So whether forecast models, NWPs, typically have Navier-Stokes equations on a globe, and you have to numerically solve them, and then you have the radiation calculations which take enormous amount of time and so on. The AI models identify patterns in the way atmosphere naturally evolves after training on 40 years of ECMWF reanalysis data, which is a combination of observations and short-term model forecasts that represent models' best and most complete picture of past weather. So you're basically generating gridded historical data by blending past data that is sparse, gappy in time and space with models which are capturing every grid point at some resolution. Then you produce a dynamically interpolated data set which can be used for training the AI models. Okay, when fed I usually Fed is federal agencies, or Fed is FBI or something, or Federal Reserves. So I got frozen a little bit. When fed a starting snapshot of the atmosphere based on the same combination of observations and modeling, GraphCast can outperform the ECMWF forecast out to 10 days on 90% of its verification targets, including hurricane tracks and extreme temperatures. We'll read about GraphCast in the next, from the Google paper, because GraphCast is a Google approach. Although it took 32 computers 4 weeks to train the AI model, the resulting algorithm is lightweight enough to work in less than 1 minute on a single desktop computer, says Remy Lam, lead author of the GraphCast paper. Is fast, accurate, and useful. Few expect traditional forecasts to disappear anytime soon, but AI is rapidly approaching the point where it could be useful. It could be a useful complement to dynamical forecasting, says Matthew Chantry, who coordinates ECMWF's AI work. Adoption might be slowed, but by unease about the black box nature of the AI, researchers often can't say how such systems reach their conclusion. So you feed it data, it doesn't need any physics, it derives the physics or patterns from the data and compares the training period and makes forecasts, but you can't always explain exactly what happened. So sausage making that scares some people who like to understand why something went wrong, how they can correct it, how they can improve forecasts for the future, and so on and so forth. But that concern can be overstated, says Chantry, who notes that traditional models are also so complicated that there is a degree of opaqueness already built into them. Ultimately, it'll come down to users. Grover says, if you're a farmer in the field, would you care about the more accurate forecast or the one you can write down with physical equations, right? If you're a user, water, agriculture, energy, health, transportation, buildings, you just want forecasts. You don't care how they were created. Okay, so let's leave this first one here, then we'll read another paper here from Science talking about learning skillful medium range global weather forecasting. So this is the name we already mentioned in terms of GraphCast, which is Google's way of doing AI forecasting, again trained with you always need data, lot of data to train an AI model, and then you let it go forward to make forecasts, which is very different. I mean, when you have numerical weather forecasting, you have a numerical model which is on the computer. You give it initial conditions. If it's weather, typically you are just initializing the atmosphere because the ocean doesn't change much. So the ocean is prescribed in some way, and you integrate atmosphere forward for a few days depending on where you are. Mid-latitude weather is now typically forecasted out to 10 days, but in the tropics, after 3-4 days it can get chaotic. And if you remember Ed Lorenz's work from the 1960s into the 1980s or so, he always talked about how small errors in initial conditions can create chaos after a few days because it's a very non-linear system. But with more data, we know now that mid-latitude physics does allow us to make forecasts out to 10 days, but in the tropics you're still dealing with convective systems that just explode very fast, so you cannot make forecasts typically out to 10 days. 3 days great, 5 days maybe, 7 days could be, and so on and so forth. So let's come back and read the GraphCast claim on AI forecasting. This little article is based on that paper, but we'll just look at that paper and read a few more technical details. Okay, see you in the next podcast.